So in this tutorial, I'm going to talk about the linearized compressed polar coordinates, or LCPC transform. So the purpose of the LCPC transform is to capture the complexity of an image. In this case, here it is the lining of a normal colon. How do we capture the complexity of these folds, right, in the form of tubes? How do we quantify it in a way that's objective and quantitative, as opposed to saying that yes, it looks normal, or it looks abnormal, or relatively abnormal. Normal colon grows like this, okay, but when it develops into pre-malignant lesions, precancerous lesions, it can look like this. In this case, this is a pedunculated colon polyp. That is a polyp that has a stalk or neck that grows out of the normal lining and forms a little polyp here, a bulb of abnormally growing colon cells. These polyps can also take on the form of serrated polyps, right? Sessile serrated, meaning it does not have a neck extending out from the normal lining of the colon, but it does grow in an abnormal way, serrated like the teeth of a saw. So how do we capture the complexity if there are varying degrees of serratedness, right, which there are? How do we objectively and quantitatively capture that complexity? The LCPC transform is also applicable to really any image or other biological system, such as here CT scans and MRI scans. The only thing that the investigator has to figure out is where to place the point of origin and what features they want to quantify. Is it just the edge? Is the degree of pores, and so on and so forth? Before we talk about the LCPC transform, let's do a quick refresher on coordinate systems. So most of us are familiar with the Cartesian coordinate system, that is the XY plane. Every point on the XY plane has an address in the form of an X coordinate, right, 2, 3, and a Y coordinate. In this case, each of these dots has an address, right, an X coordinate and a Y coordinate. There's also another way of classifying the address of each of these points using a different coordinate system, that is the polar coordinate system. So in this case, the point P in the Cartesian coordinate system has an address X and Y. But in the polar coordinate system, it has the address known as theta, this angle, and r, which is the distance from the origin to point P. Right, so point P's address in the polar coordinate system is the angle theta from the x-axis going counterclockwise, and also the distance from the origin to point P. And I just want to point out that the Cartesian and polar coordinate system can be interchangeable, right, through these conversion equations. But the LCPC works in the polar coordinate system because it's just more intuitive in terms of rasterizing an image, that is, dividing up an image into segments. Okay, so the first step in the LCPC algorithm is to overlay a radial grid onto your image. In this case, I chose the point of origin of this radial grid to be at the base of this polyp, this cartoon polyp, and where you would put the origin depends on what you're trying to measure and whether or not it makes biological sense. Now, I'm not going to go into it, but for pedunculated polyps, it would be best to put the origin down here. So this radial grid has 0 to 180 degrees of lines, okay? And what I want to quantify in this case is the degree of tubeness or tubularity of this polyp. And so for every line, I'm going to note how many times, okay, the line touches the outer or inner edge of a tube. So if you look at panel B, I've done that, for example, for these three lines color-coded in red dots, blue dots, and green dots. So a dot appears every time the radial line touches the outer or inner edge of a tube, including the outer edge of the polyp. Okay, so for every radial line, okay, I make note of the intersections, and each intersection has a distance from the origin. For example, this red dot is close to the origin, while this red dot is furthest from the origin, and each of these distances is quantifiable. And so, okay, what I do next is I sum all of these distances for all the red dots into one number. I also sum all the distances of the blue dots as one number, and same for the green dots. And so what happens is that if you look in panel C, for every angle measure, I have one value. Okay, and here I color-coded the red dot, blue dot, and green dot, what its summed value is. If you add up all the red dots, it adds up to this value. If you add up all the blue dots, it adds up to this value, so on and so forth. So here what we have is a discrete wave or sinusoid wave, right? A complex wave, all right, in the form of discrete points. That is, we do not have a continuous straight line, only points at every single degree angle that we measure. Once we have data like this, we can apply what's called the fast Fourier transform, which breaks this discrete wave into its individual frequencies that add up together that would give us this shape. In this way, by applying the LCPC transform, okay, on this image of a colon polyp, we can then derive a discrete sinusoid wave that represents the complexity of this. And if we do a Fourier transform on this discrete wave, what we get is a handful of frequencies, okay, that serve as a signature of this shape and this degree of tubularity, right? So in this way, we have simplified a very complex image, a more complex morphology, into an objective handful of frequencies that is like a signature of that kind of image. So the Fourier transform is this awesome technique that translates the complexity of a sine wave, a sinusoid wave, and breaks it down into its individual frequencies. So Joseph Fourier, right, found that that every complex sinusoid wave is essentially the addition of a bunch of simpler waves. In this case, if you add up all of these waves together, you would get this shape. Analogously, it's like if you take a page out of a book, the Fourier transform would tell you all the words that are in that book and how often they appear. The Fourier transform doesn't tell you the meaning of what that page, the content of that page, but it tells you what words are used in that page and how often. So the Fourier transform is a great way for looking at another dimension of a complex wave. When we look at complex waves like this, we're looking at it in what's called the time domain, that is time on the x-axis. But the Fourier transform changes this and shows us the frequency domain, that is, which individual sine waves comprise essentially the complex wave that we see in the time domain. And because the data that we generate in the LCPC method is discrete data points, that is, we don't have a smooth line for every point along the x-axis, we apply what's called the fast Fourier transform. So here we overlaid the radial grid onto this polyp. Here let's just first look at the outer contour. So we want to use the LCPC to calculate the complexity of the outer shape of this bulb, all right? And so here in panel B, that's what you see. Okay, so for every angle, right, what I want to do is I want to mark the intersection of that line with the outer edge, the outer contour of this bulb. And so you see here, this is in the shape of a bulb, and it's inverted compared to panel A because here we've aligned the x-axis from 0 degrees to 180 degrees, okay? But you can see that, yes, the points of the outer contour do reflect the shape, right, of the outer contour of the image. But in panel B, this is not the LCPC because in LCPC, for every angle, there can only be one, okay, point, all right? And so what we have to do is we have to, for every point that's on the same line, we add them together to get 1 point. And so if you do the LCPC transform on panel B, what you get is panel C. All right, so this is the LCPC transform of what? Of the outer contour of this polyp, okay? And once you have this discrete sinusoid wave, you can apply the fast Fourier transform to get the frequency signature that represents this, okay? And which means that this frequency signature, right, also represents the outer contour, the shape of this bulb. And so you can quantify the bulbiness, the bumpiness of a bulb, the roundness of a bulb, etc. And here in this case, if we wanted to calculate not just the outer contour, right, the complexity of the outer contour, but we want to look at the complexity of the tubeness, okay, the tubularity of this polyp, what we can do is we can, for every radial line, okay, we track the points that intersect with the outer or inner edge of these tubes, okay? And for every point in the line, we add it all together to have one number, okay, for corresponding to each radial line. So in this case, panel C is the LCPC transform of the tubiness of the image in panel A. All right, and if we apply the fast Fourier transform to the discrete wave in C, what we see is a frequency signature representing what? The tubiness, okay, of this image. Here is an example of the LCPC on a normal colon. Now in this case, I chose the origin. Instead of doing a radial center here, having lines coming out from the bottom middle of the image, I chose the horizontal axis, x-axis, okay, which is also represented by y equals 0, as the origin. And I did this because it's biologically more meaningful to measure the complexity of a normal colon fold that doesn't that forms a relatively flat shape. In this case, here in panel B, I showed you how do we, if we want to quantify the amount of tubiness, right? We look at the intersections of each radial line, or each line in this case, they're not radial anymore. Each line, with the outer or inner edges of the tubes, okay? And what we have is, in panel C, this is the outer contour, okay, of image A, all right? And you can see that, it maps out pretty well. Okay, but if you do the LCPC transform, but not just the outer contour, but every time the yellow line hits the inner outer edge of the tube, the LCPC looks like this, all right, of a normal colon. And then if you do the fast Fourier transform on the normal colon, this is what you get. So this is the frequency signature, right, of a normal healthy colon. So this provides us a quantitative objective metric to quantify the degree of normalness or abnormalness of a colonic lining. Okay, and then we can also apply the same approach to the serrated polyp. In this case, for serrated polyps, I also think it's best to assign the baseline, okay, not as one central point, but as a horizontal axis from which all radial lines emanate. And so the LCPC can also capture the degree of tubiness, or in this case sawtoothness, of a serrated adenoma. And this is what it looks like. And if you do the fast Fourier transform on this, you get this frequency signature that represents what? The tubiness of a serrated polyp. The important thing I want to point out is the arbitrary nature of where to define the base of your coordinate system. For example, if we were to I wanted to quantify the outer shape of this tumor inside this bone, right? We could place the center of our coordinate system in the middle of this tumor. In this case, we would have 360 degrees of angles at which to measure the outer contour. Okay, but this is arbitrary, right? Because you can also, right, use the 180 degree method, measuring it from the base of this upper long bone. Okay, and just have 180 degrees, okay? And why not, make the base of the radial angles here on the right side? Okay, so this is arbitrary, and it just needs to make sense biologically, okay? Furthermore, you can use a straight radial system, as I did for the normal colon and the serrated colon, and that, baseline coordinate system, right, can be really arbitrarily placed too. Again, depends on what you're trying to measure, and does it make sense? In this case, on the right, we're measuring the contour of this tumor, right, starting from the left side as the base. In this case, in the image on the left side, I put the baseline right at the epiphyseal line, so we can measure what maybe the degree of porosity, right, of the bones. What's important to keep in mind is that you have to be consistent in measuring every image, right, in a study the same way. Otherwise, your data would make just no sense. One last thing I want to point out is this extra, I think, usefulness of the LCPC for quantifying changes in spatial arrangement. This is a cartoon of the lining of the colon, okay, and oftentimes there are many ailments in which there's extra inflammation, right, infiltration of immune cells in the lining of the colon, and the LCPC can serve as an index to quantify the degree of this infiltration. Here, the cartoon, the red stars represents, extra maybe T cells or dendritic cells, whatnot. Okay, and so the LCPC method allows us to quantify the contribution of these extra stars, right, relative to the normal case that doesn't have that many or has these red stars. So this is the LCPC of this cartoon up here, and here in B, this cartoon has red stars infiltrating the lining, and the LCPC captures that, okay, and over that specific region too, all right? And what you can do is if you subtract, okay, plot 2 from plot 1, as you see in panel C, right, this area between the curves in blue, okay, serves as an index representing what the degree of infiltrating red stars, right, in this cartoon system. So this is, I think, a very useful metric for quantifying just changes in morphology, changes in the composition of cells in a biological system, or really to any image in which you want to quantify spatial changes.